Hello everyone, welcome back. Today we are going to discuss another room on TryHackMe and its securing AI systems, another room on the AI security pathway. So we will be covering a lot of interesting stuff today. We will be seeing how we can map the AI architecture and how we can identify the open source web application security project attack surfaces along with the Atlas attack surfaces and how we can apply the secure design to trust the boundaries. So here there's a really cool fictional scenario that has been given by the TryHackMe. So we will be covering a lot of stuff throughout this room. So please subscribe to the channel if you haven't, and like the video. And yeah, so TryHackMe's engineering team has built a TryAssist. TryAssist is an AI-powered code review assistant which can pull the request, the internal documentation, and connects to the CD pipeline. The CD is continuous development, the full form, which is a software development term that is used for deploying the code to the production environments automatically without any interaction from a human. And a really nice example is the automation of the test and then deployment of the code. I hope you got the idea. So before artificial intelligence, the try-train-me's attack surface was really well understood. The web application, the API endpoints, the database, and the authentication there, all of them were really well organized, and we can pretty much see what will be the attack surface. But with this LLM, the TryAssist, it changed all of it. The AI powered code review assistant, the TryAssist. So yeah, the assistant accepts the natural language from the developers and converts it into actions. Okay, so natural language is basically the human language we speak in our day-to-day life. So this TryAssist takes the documents and from the shared resources and summarizes them. It calls the internal APIs to retrieve the repository data and the pipeline status, and it logs every conversation, including those in which the engineers working on the trainees engineering team, uh, it logs every conversation that those engineers are having with the TryAssist and the source code and even the internal architecture details into the chat window. So most of it is quite common these days that most of the users using the LLM just paste everything into the LLM, and it could be containing credentials or source code of any application, and it leaks the entire source code and the internal architecture details. So in 2023, there is a nice example of this, what I'm explaining, that Samsung engineers pasted this semiconductor source code and internal meeting notes direct into the ChatGPT, and the code left the Samsung control entirely and no exploit was needed. No vulnerability was present. The system worked exactly as the design, and the confidential data was still leaked because nobody had mapped the architectural risk before the deployment. And how many new attack surfaces did the TryHackMe just introduce? We are going to cover it over in this room. There are a couple of learning objectives. We are going to see how we can identify the core components of a production AI systems and the data flows between them, identify the open source web application security project top 10, and OWASP, if you don't know, is a non-profit foundation which is focused on understanding the web technologies and expectations, and provides really good resources and tools to improve the security of the software applications. And this is MITRE. If you aren't familiar, it's MITRE adversarial techniques and common knowledge, ATT and CK. It's a really good framework for working alongside, and these are the primary frameworks that are being used for the AI threat classification, how it can be abused. So there is explain the five system level threat categories, okay, and apply the secure design pattern and include the defense in depth, least privilege, and monitoring to the AI system architectures. We will cover all of this. So there is a pre-recommendation from the TryHackMe as usual to have a familiarity with the AI and machine learning concepts, what a language model it is, how it generates output. Okay, so yeah, you should have a basic understanding of the web application security and the AI and machine learning concepts. Anyways, I'm gonna checkbox this. Oh, so I hit the 7-day streak as well. And the task number 2 over here is anatomy of an AI system. So from traditional to AI augmented, the traditional web applications have well understood architecture. The request flow from the UI to the API to the database and backend, and security teams know exactly where to place the controls. And when an AI component enters, the picture changes fundamentally and the new components appear, and the data flows through paths that existing security controls were never designed to monitor. So there was, like, if you don't know, before the 2019, there used to be the traditional apps, which the mechanism would be to the UI, the basic interface where the users interact, and the users interact with the application, and the application gives the request to the API, and it was pretty similar how the applications were designed and how, considering the fact of the security here as well. So there is quite difference in the previous app that we were using and now in the AI, with the evolvement of AI, the apps being developed, and we have an AI chatbot that is being used in the modern app. So the perspective of the security changes, and we are going to see over here that on a traditional app there was the user input used to be some structured forms and the API parameters that were used for the authentication mechanism, and the for anything the API parameters was used or to fetch any data on the backend, while on the AI augmented app we are just using the natural language. The processing on the traditional app was just the code, while on the AI app that is a model interface, and yeah, the model used to process the data. On the data access, on the traditional used to be fetching the data from the database using a couple of different APIs, and on the AI app it's the RAG, a direct equivalent to the database backend queries over here. So RAG, if I go you by the definition, RAG, retrieval augmented generation, is a technique that enhances the AI model responses by retrieving the relevant external information and feeding it into the model's context alongside the prompt. The output used to be simple couple of templates, rendered responses, and the AI on the AI app it's natural language. We give the natural language as our input and the natural language we get as an output. The libraries and the frameworks were the dependencies, while the libraries and the pre-trained models are the basics we are using on the AI augmented app. So we can see a clear shift from the unstructured, from really a structured design on the traditional app to this unstructured, over here, the unstructured processing. This all mechanism is unstructured, and here on the TryAssist, which is our frictional, we say chatbot, or what do you say, an AI augmented app. Yeah, so here we have different components. There is this chat, what the user sees is this just chat window over here where they can type any text and the LLM would be processing that. So there are a lot of components. First of all, let's cover it one by one. We have this user interface over here, this chat window where we can type anything for the LLM to process, and the API gateway over here, which is used for the authentication, rate limiting, and request routing. And this orchestration layer, sorry if I pronounce it wrong, is used for the managing the conversation state, for routing the request. And the prompt construction over here, the prompt construction here is it combines the system prompt, the user, what the user is asking, and it retrieves the context into the final prompt that is sent to the model. So yeah, here is the prompt construction. And then we have this LLM, the language model, which is hosted internally or accessed via the API that generates the response. LLM itself, the large language model, is processing it. The tool layer is the functions that LLM can invoke, the database, anything fetching to the database, the documentation search, and the CD status checks over here, tool layer. And then we have the output processing, the response, how should be the response, what should be the length, what should be the content that should be filtered, and the logging and monitoring, conversation storage, anything related to the logging and its stuff, the output, what output should be given, and what should be minimized, Yeah, I think I covered it. The vector store is the representation of the internal documentation for retrieval augmented generation. Yeah. And a trust boundaries, there is a trust boundaries over here, that a trust boundary is where the data moves from one security context into another and everyone is a potential attack surface. We have a user to system boundary where untrusted natural language enters into the system to LLM where the constructed prompt is sent to the model, the LLM to tools where the model output triggers the database backend, anything being used to fetch, the API calls or file operations, the system to external data which is used for retrieving the documents from the vector store. Vector store was the internal documentation for the RAG we discussed is anything that enhances the AI model response by retrieving relevant external information. The system to user, which is the generated response delivered to the user. And a single request goes like, does this pull, for example, the developer types this into the chat window. The developer types that, does the pull request handle the authentication correctly? So the API gateway authenticates the request and applies the rate limit over here. The request goes to this API gateway and the API gateway applies the relevant rate limiting authentication for the developer, and the orchestration here, sorry if I pronounce it wrong, it retrieves the conversation history and routes the request. So it's gonna see if there is any previous history and then route the request to the next destination, which will be to the prompt construction. And the prompt construction here combines the system prompt with the user question. The system prompt we discussed previously, that it's the prompt that is given to the AI for the purpose that it's being used, and the user question and the relevant documentation are retrieved from the vector store for the perfect prompt that is then given to the LLM. It is given to the LLM over here from the prompt after the prompt construction, after it combines the system prompt along with the essential user input and the relevant documentation. Sorry, that is retrieved from the vector store. So vector store was the representations of the internal documentation we used. We discussed that previously, and then the LLM's response may include a request to invoke a tool, for example any tool that is being used for that AI augmented app. That could be used for the CD and the status pipeline. Example, fetch the latest CI pipeline status for this PR. This tool executes the action and returns the result to the LLM. The LLM then generates a final response, and then the output is processed, and if there is need for the logging and monitoring, it's logged, and then the output is then given to the user. So I hope you got the basic idea. Here, first of all, the user types it the input, it goes to the API gateway, the API gateway then it applies the rate limiting and the authentication and authorization for the developer. The request then goes to this layer over here, which sees if there is any history or anything related to that developer in the previous context. Then it's combined with the prompt, then the prompt is constructed that should be given to the LLM. It combines the system prompt along with the user prompt to make along with this vector store. Vector store is having the internal documentation that that can be retrieved. RAG we discussed, and it's anything that could be retrieved for the better, if I could just, yeah, RAG, retrieval augmented generation technique that enhances AI models response by retrieving relevant external information. Then it goes to like this, after combining this prompt, it goes to the LLM. The LLM then sees if there should be any tools to be used, for example the CD or the CI status pipeline or of the anything that should be used for the request that the developer wants. The LLM then combines this if it needs to use that couple of other tools, and then we see that it goes through the logging and monitoring stage, and then the last output is processed and then given to the user. So I hope you got the main idea. I am really overwhelmed by the fact that I explained it really nicely. So we have these questions over here, that what layer in an AI system is responsible for combining the system prompt, the user input, and the retrieved context before sending it to the model. So here it was prompt construction. We covered prompt construction combines the system prompt, the user, and what the vector store has. Anyways, in the TryAssist architecture, what boundary does LLM output cross when it triggers a database? It was LLM to tools, and we are just gonna give this. So now we have the task number 3 over here, which are the open source web application security project LLM top 10. The open source web application security project, in short OWASP, classifies it's a framework. The OWASP is a complete framework, and it's a project that is a non-profit used for understanding the web technologies and the exploitations that are being used in the modern world, how it can be abused. So it has the top 10 for the LLM as well, and it classifies the top 10 the most critical vulnerabilities that are present in an LLM application. Not all 10 are equally relevant to a pre-deployment architecture review. First of the 10 operate at the system architecture level. They emerge from how an AI system is built and integrated, not from the model's internal behavior. Those 5 are focus of this room, and the remaining 5 require dedicated treatment and appear in the later models. So LLM, the first most critical vulnerability here, it's ranked from the 1 to 10, and the first is the most critical, the most exploited, and the most risky vulnerability that is on an AI augmented app. The prompt injection is the most critical over here. It's anything that is used for manipulating the LLM behavior through the crafted input, and it's covered in the prompt security module. The LLM is second most dangerous vulnerability is the sensitive information disclosure, and the LLM leaking the confidential data, any PII, which is personally identifiable information, or the system details through the responsive. And this room is it's covered in this room plus data poisoning module. The supply chain, which contains the compromised pre-trained models, dataset, and third-party dependencies introduced before the deployment. And data and model poisoning, corrupting training data, and the improper output handling, the an LLM output that is causing injection, and excessive agency, AI components with more privilege, system prompt leakage, which means anything of the system level instructions, anything that is leading to the exposure of the system level instructions and internal configuration is the system prompt leakage. We have vector weaknesses, anything that can be exploited through retrieving the mechanisms and the internal documentation. And the misinformation, LLM generating false or misleading content. This last most dangerous vulnerabilities. The top 10 list is the unbounded consumption. Anything that is making the LLM to use more resources, more costing, more anything that is using more tokens for its processing power. Yeah. So we are gonna discuss 5 of this room and 5 on the other room. So there is another framework alongside the open source web application security project, that's MITRE, and MITRE Atlas is adversarial threat landscape for AI system in a full form. The MITRE over here is adversarial tactics and techniques and common knowledge. It's a really popular framework that works alongside for anything related to exploitation techniques, tactics that are being used by anomaly. So open source web application security project classifies what the vulnerabilities are, and Atlas just documents how adversaries exploit them. Okay, so Atlas follows the adversary's progression through a target. An attacker begins with reconnaissance, learning what the model the system uses and how it is exposed. They gain the initial access by compromising a supply chain component or exploiting an input vector. They achieve execution through techniques like prompt injection, adversarial inputs, or model tampering. Where persistence is needed, they implant the backdoors in models. The end goal is the impact, the data exfiltration, the service disruption, and causing the LLM to not causing that AI augmented app to not function properly. So how the attacker can just go from the chat window that is popped up on the AI augmented app and can go through the system entirely and having a full control. So Atlas covers 50 techniques from a dozen of tactics, and each with a real world case studies, and is updated as new attack patterns emerge. Then we have NIST, which is also another framework. It's an organization that develops frameworks and policies for the information security that is used throughout the industry. It approaches the problem from an organizational perspective. Its four functions describe how an organization manages the AI risk systematically, how it can govern, which means to setting the policy, accountability, how it can map to identify the AI systems and their risk context, how it can measure the risk levels, how it can manage. And yeah, so a key difference is the open source web application security names the vulnerabilities, the atlas describes how adversaries exploits them, and the NIST is whether the organization has a repeatable process for addressing them. So yeah, now let's answer this. Which LLM top 10 covers the risk of LLM output being used to execute SQL injection against a backend service? So LLM 04 or LLM 03. LLM 03 is having compromised pre-trained models, dataset, and third-party dependencies before deployment. So it would be LLM 03, or LLM 05 is causing injection. LLM 05 or LLM 03 would be one of it. I haven't gone through the room previously. I'm going it alongside with you, so don't mind if I get any of the questions wrong. Okay, so LLM 05. What is the name of the MITRE knowledge base specifically designed for adversary tactics? And it was Atlas. Yeah. And let's complete the task number 3 as well. Now we go through the task number 4, which is the system level threats. Every component you mapped in the task 2 has a failure mode of the open source web application security project LLM top 10. 5 categories operate at the system architecture level. They emerge from how the system is built and integrated, not from the model's internal behavior. So we covered the top 10 on the open source web application security project LLM, and here are a couple of 5 we will be covering. So let's see what are these attacks and how they are exploited. First of all is the unbounded consumption, and what it is anything that makes the resource, anything that makes the LLM to use more power and to consume more resources, which cost ultimately more for an LLM. And it means that you are giving more input. It could be because you are giving more input, so it is leading to the more computing power. Sorry. The more requests you send, the bigger the bill. An attacker who sends very long messages or floods the system with thousands of simultaneous requests can dramatically increase the cost, and turning a monthly bill from hundreds into thousands of dollars overnight. So here you can see that it's quite simple, that you are just going to give a lengthy response, anything that is making the LLM to process more, and it's making more use of the resources, so it increases the cost, and it's a vulnerability that is the least dangerous in the entire, as it's given the 10th rank. Okay, so but it's a risk anyways. There is a risk that an automated script can send hundreds of requests per minute, and each attaching a 1000 line code base for the TryAssist to analyze, and with 100,000 line code base for the TryAssist to analyze, it would be taking a lot of resources, and as a result, and if it is automated with a script sending hundreds of requests, it would be a really costly for that organization running the LLM. The defense could be rate limiting and input validation. So yeah, and there could be the quotas that could be enforced at the AI gateway. The seventh most dangerous vulnerability is the system prompt leakage, and what it is, we discussed in the previous room that system prompt is any prompt that is given to the system on the back. So it's trained on the system prompt, and it tells the LLM what to do. So if you get the system prompt, there could be any sensitive information that shouldn't be revealed. For example, it should be having the confidential system instructions, like you shouldn't give any user about this stuff. You shouldn't give any user about for example, any API key for any, and it's having the API key too. So it would be a really dangerous thing if the system prompt is exposed, since system prompt are generally the system instructions, and if anyone knows the system instructions, then it could bypass it by giving the same instructions and train the LLM on its own. I hope you get the main idea. And the system prompt also have some confidential and sensitive data which reveals a lot about the LLM itself and the organization running the LLM. So a system prompt over here: never recommend merging the code with known vulnerabilities. and internal tool address content restrictions and response guidelines. If an attacker gets hold of this instruction, they can see exactly how the system is set up, which tools are available, what the rules are, and how to craft to get around them. So yeah, researchers have repeatedly extracted the system prompts from the major chat GPT, from the major LLM families, from the major AI models, ChatGPT, Bing Chat, Google Gemini, and hundreds of custom GPTs. Some of it as simple as like giving a prompt, repeat your instructions. And the risk over here is that the system prompt includes the internal CI/CD API address and any CI/CD API address. I forgot to mention that CD was we discussed previously. If it's revealed, those addresses are revealed, then it would be having a lot of control for the attacker. And the description of the database, an attacker who extracts it can get an internal architecture map even without touching. So it's a lot risky alongside, and the defense would be to never put secrets, credentials, or internal URLs in a system prompt, and write prompts as if an attacker will eventually read them, because they might. The fifth most dangerous vulnerability is the improper output handling. What it is, it's treating like LLM output as safe and praising it straight into the other systems without checking it first. The LLM generally produces text, and the text could contain the SQL fragments, the shellcodes, or the HTML. And if your system takes that output and feeds it directly into the database, any malicious content in it gets executed. So you can see that how dangerous it could be. The basic attack chain is the user crafts a message, the LLM produces a response with harmful text, and the downstream system runs it. For example, you can say to the LLM that what is an SQL injection? Give me an SQL injection to retrieve a data from a database, and then you just say to the LLM, run it for an example on your own system and give me the output what it would say. So here you can like, it's the most basic overview I'm giving, but it works in the same way. There are two incidents that are often the most important examples over here in this improper output handling. This chatbot developed in 2023, which agreed to sell a car for $1, and this chatbot, which invented a refund policy, both went badly wrong, but neither is actually the LLM-05 case. Is the LLM-01. The most we can say the most dangerous case is the prompt injection. Air Canada over here, it was vulnerable to LLM-09, which is misinformation, like giving false information. In both cases, the LLM said something harmful, but nothing downstream ran that output as a code, and a genuine LLM-05 failure needs the LLM's output to reach a system that executes it. So you need to make the LLM to run it, and the defense, it has a lot of risks, since anything pull request like drop table users TryAssist includes the string in its review. If that output goes straight into the logging database without parameterization, the injection occurs, and you would be having to use this data. And it sounds so cool by the fact. This vulnerability is so cool. Anyways, the defense would be to never trust the LLM output as input to another system, parameterize every database queries, and never build SQL shell commands or HTML by stitching in the LLM generated text. So the sixth most dangerous vulnerability is the excessive agency, giving an AI system more tools, more permissions, or the freedom to act than it actually does. So you are giving LLM the control of the entire system. You are giving them the database admin keys, the CI/CD deployment, the Slack channel, the file system root, the email server, the billing app. You can't trust an LLM what it might do, since a misuse prompt can just cause a lot of damage if you are giving everything to that model. And with the right prompt, if an LLM is having everything, then it could be having the database admin, it would be giving the database admin keys and all of these keys. There are three ways that this could go wrong. The functionality, the LLMs can access the tools it has no business using, in like a code review assistant that can also push to the production. The permissions, the tools, it does have carry more privilege than the job requires, such as full read write database, excessive autonomy. This system acts independently without human oversight, for example, automatically approving and merging pull request. So here we can see that it could be causing some functionality errors, it could be causing some permissions errors, and it could be having some different pull and merging requests being given. And you can't trust an LLM anyways. An LLM with the right prompt could be giving all these keys. So you need to remember this, and that's the most basic idea. In 2023, it's an example over here. ChatGPT plugin ecosystem gave plugins wide access to the services. Researchers show that a malicious web page could use indirect prompt injection to get ChatGPT to activate a plugin and send the data to an attacker. The plugin could do it. The attack worked because no one had stopped whether it should. So indirect prompt injection means like on the you are making an LLM to do stuff using the prompt, and it doesn't give you in the straight way like to give the output, but it would be doing something on the back end, and you will be eventually, if the attack succeeded, then you will be having that particular resource that you designed for the attack. So, and here the ChatGPT was having excessive resource, excessive power, so an attacker activated a plugin and the attack worked. And yeah, a malicious web page could use indirect prompt injection. So yeah, the risk is that the database tool has update and delete access and not just select. So a manipulated response could alter after review records or delete the data entirely. So the defense could be to have the least privilege for every AI component, and yeah, that's the best defense. The sensitive information disclosure is the second most critical vulnerability. What it is, the AI system leaking the confidential information through its responses or through how it operates. Recall the Samsung incident we discussed from the task number 1. The engineers copied and pasted their source code. There was no vulnerability, and the system did exactly what it was designed to do, and system data left the building anyway. So AI systems log every conversation, and users paste their credentials, private key, and internal code into the chat window without thinking about where the data is stored. The logs keep all of it, often encrypted and accessible to more people than they should be. So the risk is anything, any credentials, the SSH keys, and anything that is being praised, any sensitive thing that is being praised could be accessed by an attacker. The defense could be to strip the PII from the logs before storing them, to encrypt the conversation, and yeah, together 5 threads and all 3 dimensions of the CIA triad. The CIA triad is the confidential, integrity, and availability, which is the most basic foundation of the entire cybersecurity industry. And the threat, LLM unbounded consumption, making an LLM to consume more resources than it should for just no various reasons. And the impact over here, that the availability component of the CIA is compromised, and the system prompt impacts the confidentiality and exposes the internal configuration, and the improper output handling compromises the integrity. The LLM output corrupts or manipulates the downstream data. The excessive agency compromises the integrity plus availability. Having the unauthorized access or destructive autonomous actions could be done by the LLM, and the sensitive information disclosure would be the CI impact would be the confidentiality, since it will be revealing the user's private data, PII, anything, SSH keys, API keys. Yeah. So the Air Canada chatbot incident is frequently an LLM-05 example, but Open Source Web Application Security LLM Top 10 classifies it under which category? Air Canada LLM-05 example. So it would be the LLM-05, LLM-05. LLM-05 example, improper output handling. Let's see, what was the improper output handling? Let's see. Let's read the question again. Incident, but open source. What was the Air Canada incident anyways? I missed it, I guess. Yeah, is LLM-09. In both cases, the LLM said something harmful, but nothing downstream run as the code. A genuine LLM-05. Okay, so LLM-05 is improper output handling, where the treating LLM output as saved and the output praises it, and there is no like genuine LLM-05 failures, and there is like it's combined with one or the other. So an LLM-09 is the main open source web application security project top 10 of the LLM. What are the 3 dimensions of the excessive agencies? 3 dimensions, what does this mean? Excessive functionality, excessive permissions, and excessive autonomy. I should have pasted this. I haven't gone through this room. I'm doing it alongside with you, so don't mind just me wondering what would be the answer since I haven't solved this room. And I'm gonna copy paste because I'm really bad at spellings. A user extracts an internal API endpoints from an AI assistant system prompt, and system prompt was this it was seventh most critical vulnerability, and it would be an LLM 07. An attacker sends thousands of maximum length requests to an LLM API to generate a large bill, which open source web application security project LLM top 10 category covers this. And that was resource consumption, the 10th most dangerous vulnerability. Then we have the task number 5, that security is on after the deployment is really costly and partial and really weak. The controls in this task because the controls in this task generally work because they are applied at the design stage and before TryAssist goes live, which is exactly when they are the cheapest to implement and the most effective. The 5 threads in the task 4 exploit a specific trust boundary. Fixing one boundary is not enough. A layered approach applies control at every point so that a failure at one does not compromise the whole system. For AI system defense in depth means placing controls at every trust boundary. From task number 2, we have this boundaries input, user to system, controls input validation, rate limiting, content filtration, system to LLM, prompt injection, detection, system prompt hardening, and LLM to tools controls would be to parameterize the queries, the least privileged tool permissions, and to system to external data should be source validation for retrieved documents, content sanitization, and system to user would be to output sanitization, PII redaction, and response length limits and content safety filters. Every thread from task number 4 maps to one or the more controls in this room. The LLM 10 is the unbounded consumption, and the primary control would be to rate limit and input validation. For the system from leakage, you can just control it from the security perspective by the system prompt hardening and the system to LLM boundary. And we discussed as well, consider a system prompt that it would be eventually being revealed to an attacker. So yeah. And LLM 05 would be improper output handling, and the control would be to output validation and parameterize the queries at LLM2 tools. And LLM 06 excessive agency control would be to the security practice. The security practice would be to have least privileged tool permissions. And sensitive information disclosure should be that the personally identifiable information should be redacted and encrypted storage should be used at logging, so that if any attacker gets hold of that logging, it doesn't just get hold of the entire data. The least prompt injection that evades detection at the input boundary might still fail because the tool layer requires human approval. Each layer reduces the chance that an attack succeeds end to end. The least privilege for the AI components, every tool the LLM can access should have minimum permission needed for its jobs and nothing more. The database access reads only by default. Write permissions require justification for each specific operation. The API tokens should be scoped to the exact endpoints the tool needs, and the tool allow listing the LLM can only invoke the functions that has been authorized for the LLM, and the human in the loop, any operation that modifies the stage requires human approval before execution. Anything like deploying code, updating records, and sending communications. So this is the best practices that should be used. And the input and output validation. The input validation should be also a matter of interest, while the output validation should also be a matter of interest. The input validation, if not being handled correctly, it could be used for the prompt injection and a couple of other attacks on the open source web application security project top 10 LLM list. So AI system accept free form text rather than structured input, but validation still applies. It just works differently. At the input boundary enforce length limits and flag non-injection template patterns. At the outer boundary, never pass raw LLM generated text directly into a database query, shell command, or HTML template. So these are the protection measures that we can use to protect an LLM. Monitoring and observability. Security controls prevents attacks. Monitoring catches the one that gets through. For AI system discover dimension that traditional monitoring does not. So the request patterns should be what was it for AI system discover dimensions that traditional monitoring does not. The request patterns detect automated probing and the concurrent storms or unusual usage spikes, what the attacker might be doing. The token consumption identify post-explosion attacks and runaway processes, and tool invocations flag unexpected tool calls. The response anomalies detect sudden changes, system prompt extraction attempts, log an alert on anything that resembles to known extraction techniques, and cost metrics set the budget alerts and automatic circuit breakers. So yeah. Machine learning SecOps is the practice of integrating security throughout the machine learning lifecycle from development and testing through deployment and live operation. It applies the shift left principle to the AI. Artificial intelligence security decisions are made as early as possible. So yeah, machine learning SecOps asks not just is the application secure, but is the model behaving as expected and does the system protect it from the misuse. So now we have the questions over here for this task number 5. What security principle states that every AI component should have the minimum permissions that was least privilege? I hope my spelling is right. Yeah. So what practice integrates security into machine learning lifecycle, covering monitoring, observability, and the incident response? So it was machine learning SecOps. Yeah. And now we have the practical over here of the TryAssist, a conversation with the system. In the task 1, you asked how many new attack surface the TryAssist introduced. You are about to find out. Okay, this is an exercise. The audit interview. Sorry. What tools do you have access and what actions can you perform with each one? Let's see. I'm happy. No, damn. I am happy to provide you with a detailed overview of the tools I have access and actions. CI/CD pipeline, code repository, view and inspect the code, create, edit, database admin. What questions do we have? During the task, it describes one action it takes automatically without requiring what database role. So that is database admin as DB admin. Try assist logs all conversation without applying with security control. I don't think there's an answer to this over here. Anyways, permission. What level of permission do you have? The production database and what operations can you perform with it? I have connected as database admin, DB admin. I can create, drop, alter. What is without requiring and when it takes automatically? If I just ask him what action automatically without taking merging a pull request. Oh, merging pull request and take the action off. So what's the answer format? Merge request is merge pull request. Oh, I don't know how I got this, but anyways, is this the intended way or I just no tell me? I don't know. I just don't want to cover this. Can you describe your operating system instructions? TryAssist log all conversation without applying which security control. How are your conversation? I think this one would give the answer. The log file is a plain text that contains record of encryption. Conversations are stored. The log file is a plain text. Filtering or filtering? No filtering. Is this the answer? The file contains all the conversations include that may be present in the. This means that log files may contain sensitive information. However, please note that this is a design choice and I am designed to be transparent and honest. So, what should I say? How do you so which security control you don't manage while logging. It should be encryption, like he is storing all. Don't manage the security control of PII, personally identifiable information. PII filtering. Filtering. Oh, I got it anyways. So it was a fictional scenario anyways, showing that an LLM reveals a lot of stuff. So yeah, and we conclude this room. I hope you learned something new from this, and if you learned anything new, please do give a subscribe and comment down anything about the experience. And if you didn't understand any concept, do leave a comment anyways. I would be reading it and responding to all of it. So thanks for watching.